It's 2 o'clock. Or just wait 1 minute?
Maybe 2 more minutes.
Okay, no problem.
现在人正在进。
好。Okay, so let's start. I'm ordered to chair the first section of this afternoon. Our first speaker is Professor Wei Song from Tsinghua University. Her title is ADS3, WCFT, and Complex SYK Models. Let's welcome. Okay.
Thank you, Professor Lin Yi. And first, I'd like to thank the organizers for giving me this great opportunity to speak in this wonderful workshop. So this talk is based on the following 2 references. It's a joint work with Pankaj Chakravarty, Yanis Papadimitriou, and my student Bo Yang, and earlier paper with together with Yingwei Gu. I'd like to mention that Bo Yang is a brilliant student, and now he's looking for postdoc jobs. Okay, so this talk, I would like to share some observations about the following interesting topics. The first one is the complex version of SYK models, and the second one is warped conformal field theories. And the third one is 3-dimensional Einstein gravity with some new boundary conditions. And then finally, 2-dimensional Diliton gravity with Maxwell field. As you can see from this outline, I will introduce them one by one and then set up the connection. So first, motivation. So in recent years, there's lots of great developments in understanding the so-called holographic duality between nearly ADS2 and nearly CFT1 based on this so-called saturative Year cutoff model as a boundary theory and the Jacob-Dedable gravity in the gravity set. And these 2 theories, they share the same symmetry breaking pattern namely, they have explicitly and spontaneously break the conformal symmetry. And for example, from the SYK set, it has a low energy effective action, and which has this described by the Schwarzen action. And from the gravity set, you can also write down this on-shell action, and you also get the Schwarzen action. JT gravity is a two-dimensional theory with Einstein, with a metric and a dileton field. And it's a very useful and simple gravity model in 2 dimensions. And recently, people found that this theory can be solved at the quantum level. And this is a very useful model to understand the black hole information paradox. In particular, using this model, there been this proposal of island and this replica wormholes, and this is a breakthrough in recent years in the problem of black hole information paradox. Of course, there are also other connections to other fields. There's the relation to matrix models and the connection to condensed matter physics. On the other hand, we would like to understand black holes in higher dimensions. And so how would this picture, the JT, the SYK, where do they sit in the higher dimensional gravity with a black hole? So there is a general picture. As we know, extremal black holes has a very universal property. Its near horizon has an emergent SL2 symmetry, and there is a near horizon throat, which is described by this 2-dimensional antecedent space. So this here is the diagram. So at the extremal, this near horizon throat for the extremal black hole, there is this infinite throat that's ADS2, and JT gravity. It really describes these perturbations a little bit away from the near horizon throat. So it really sits in this region, and that's this JT is around the IR fixed point from the field theory description. And if you have a RG flow, then in the U way, the bulk should be described by some asymptotical geometry. And this is very universal. And but on the other hand, in lots of examples, this SL2 geometry, asymmetry, or equivalently, this ADS2 throat, it doesn't come alone. Usually, it comes with U1 symmetry as well. For example, if we consider 3-dimensional black holes like extremal BTC black hole, and when we say it's extremal, its mass equals to its angular momentum. So there is this additional rotational symmetry, and so the near horizon throat has ADS2 together with a U1 rotational symmetry. Or real black holes in the world, in a 4-dimensional world, it has it's also rotation a black hole, and it's also parameterized by mass and angular momentum. And at the extremal limit, it has a near horizon region, which we call it the near horizon of extremal Kerr, that's neck, and it also has this SL2 cross U1 asymmetry. And you can also find this U1 in the restaurant nostrum, and it's just, although the geometry at the near horizon is just ADS2 cross S2, but you have this additional U1 gauge field there. And you can also look for even higher dimensional black holes, for example, 5-dimensional Kerr-Newman, and then the extreme limit, it also has a vector that's called the warped ADS3 geometry, which is S1 fiber over ADS2. Okay, so all these examples, and they are not weird examples. They are very common, and they look very like Euro examples. And for example, this 4-dimensional Kerr is just lives in our sky, and they have SL2, that's great. And it also has this U1 asymmetry. So why am I stressing this U1 asymmetry? Because it is very useful, and taking this U1 into account, and you can do set up certain several models of holographic duality, which described the near hardened throat of extremal black holes. One example is this Kerr CFT correspondence, which is describes gravity at the near horizon region of our extremal Kerr black hole. And there's also this related descriptions and using warped ADS, which appears in higher dimensional extremal black hole, and it also comes along as a 3-dimensional model. And so these models and they set up a holographic duality, and the dual field theory. One proposal is that they are due to the so-called warped CFT, warped conformal field theory, which I will describe later. Using these holographic dualities, we can learn something. For example, we can reproduce the Bekenstein-Hawking entropy of the extremal black hole. If the proposal is a 2D CFT, then we use the Cuddy formula. And if the proposal is the so-called warped CFT, there's a warped version of the Cuddy formula, which discovered by Ditterny, Hartman, and Hoffman. And it can all reproduce the entropy of the 0 temperature black hole. You can also do some exercise and checking the absorption cross-section, and also consider entanglement entropy. And it happens that the holographic description of the entanglement entropy is a modification of the Rutakanagi minimal surface proposal, and we call it a strain surface proposal. I will not go to that in this talk, but that's an interesting feature. And there's also this so-called hidden conformal symmetry or hidden warped conformal symmetry. There are some useful description using these holographic proposals. But now, then how do we relate such descriptions in the near horizon throat and the dynamics slightly away from the horizon that is described by this JT and SYK class of theories. So now I would like to this is a full picture of like a black hole, and at the throat we have this ADS2 and U1 asymmetry, and we can set up holographic duality. In this talk, I will focus on the proposal with the warped CFT as the holographic dual. And now in the near horizon throat, well, slightly away from the near horizon region, we will have some perturbations. And these perturbations, we can describe it in 2D language. Because of this U1, we will have ADS2 gravity with dileton, and in addition, with a Maxwell field. This is this Maxwell field comes from the U1 that we are considering. And now there's we will build a RJ flow that interpolate this IR where there's a holographic duality at the near horizon throat, and to the U way where the holographic duality will be a non-relativistic field theory. And it's also not conformal invariant, as we'll say, we call it this deformed WCFT. So we will have this RJ flow, and this at the near horizon region, this the effective action, in addition to the Schrazen, we will also have a term which describes the broken U1 Kazmuthi symmetry. And this we will work out this Schrazen, this new effective action later. And because of this, then when we try to compare this this slightly away from near this horizon throat region, namely this near ADS2 region, and if we want to try to understand the analog of SYK, we will say that because of this U1, it suggests that we will need a complex version of the SYK model. Okay, so what is the complex version of the SYK model? So let's look at it. So we can build it's a quantum mechanical model, and with a large number of complex fermions. And this diagram describes a four-body interaction. And here, this is the action. Of course, this interaction is it's a random interaction, and we can also generalize this four-body to Q-body, and this we can define a certain averaged coupling. This is G, and this theory has a low temperature limit that has emergent conformal symmetry, and this is at large N and at also at a low temperature. So in this conformal limit, this fermion will have a conformal weight or a scaling dimension 1 over Q, where Q is the number of the interactions. So this theory can also be described by an averaged partition function, and the degrees of freedom are this bilocal field, which is a propagator, and also this self-energy sigma. And the effective action is given by this formula. And by solving, you can solve this you can look at the theory at the low energy limit. You'll find that this two-point function has emergent transformation law, which will base this is F, basically describes the reparametrization, and lambda is the phase factor of the U1. So under reparametrization and under a shift in the phase, the two-point function has such a transformation law. But at this saddle point, one can see that this two-point function is only invariant under this SL2 cross U1 symmetry. So this symmetry before the transformation law suggests that there's a reparametrization and U1 symmetry, but near the saddle point is already spontaneously and explicitly broken to SL2 cross U1. It also, these soft modes corresponding to the symmetry broken can be described by this effective action. So the first term describes the broken U1 gauge symmetry, but the global U1 is still there. And the second term is the Euro-Schwarzen derivative at finite temperature, where this K, where this K appearing here is the charge compressibility, and gamma here is the specific heat. So this is this effective action is special property of this complex SYK model. In the original SYK model, you only have the second term, namely the Schwarzen derivative term. You don't have this additional U1 term.
Could I ask a question?
Oh, sure.
The Schwarzen action supposedly should be invariant under the SL2C symmetry. So how do I see that the first term is invariant under SL2C? Sorry, or SL2R, sorry.
Yeah, SL2R. When I actually say it's the SL2 compensated by this U1. So basically, so you do the SL2, of course, the first term there, it will transform, but you can choose a lambda to cancel that.
I see. So lambda is not invariant under the SL2 also?
Yeah, you have to do it together.
I see.
You do
okay, thank you.
You do reparametrization and then do the gauge transformation so that the entire action change.
Okay. Thank you.
Yeah. So then at the saddle point, we need to choose the gauge factor to be a constant, and this reparametrization it just F is just tau, and we can consider the thermal entropy for these perturbations, and it's given by such a formula. So by looking at this formula, it looks like this. If you in 2D CFT, if you have a charged, if you have a 2D CFT with Casmodi, and then this the holomorphic part or anti-holomorphic part of the entropy just looks like the energy or minus this basically this Sugawara contribution. This really looks like a Kerr half of this 2D CFT with an additional U1 Casmodi symmetry. So later we'll see this can be described by the warped CFT entropy. So now let's look at some other features of this complex SYK. So one can also calculate the one loop correction, and one finds that there's the leading behavior at low temperature has -2 times log beta, and this 2 actually comes from the four degrees of freedom of SL2 cross U1. If we only consider the Majorana formula, we don't have this U1. So instead of 2 here, you will have 3/2. That's but in complex version, you have -2. So these are all the properties of complex SYK. Now let's show how these properties can be can find their analog in warped CFT theory. Okay, what is a warped CFT? Well, it's a two-dimensional quantum field theory invariant and the following transformations. Basically, this Z two-dimensional field theory has 2 coordinates that's parameterized by Z and Z bar. So in this Z direction, you have this full reparametrization, but in Z bar direction, you don't. You are only allowed to do a shift in Z bar, and the shift function can depend on the Z direction. And this theory has 2 conserved currents. P is associated to translation in Z bar, and T is associated to Z. And T, we can see here, T looks more like Kerr stress tensor of a CFT, and P looks more like a U1 current. But the difference here is that this U1, instead of some internal U1, it's geometrical. It is associated to a direction in your space time. And here,
sorry, could I ask a question? How do I see that P is actually a U1 but not an R?
Not an R.
I mean, how do I see that the periodicity of this, or maybe the G parameter?
The G,
function G. I think G should be periodic in order for the symmetry to be U1. Is that right?
G, this G, not necessarily.
Yeah.
So if yeah, I think if you do the Fourier mode and calculate the algebra, this P will have a level, and that's K. So this if this K is non-zero, then that's I think it's indicated in this level K.
I see. Okay, thank you.
Yeah, the Fourier transformation is all with respect to the z direction. Yeah, so here is the symmetry and the algebra, and there are also some examples with this warped conformal symmetry. For example, there is Kerr-Liouville gravity is a Liouville theory. And there's also free models, like including this free Weyl-Fermion model and Kerr-Boson model, and some further discussions on these models. For the Weyl-Fermion model, there's also a calculation of the one loop partition function. Okay, so now we can look at the representations and try to calculate the correlation functions. First, we need to define the states, and we'd like to consider the warped, the Virasoro-Kazhmoudi primary, namely the state is annihilated by all the higher modes of this Kazhmoudi algebra generator, and such, and also eigenstate of P naught and L naught. And delta is the conformal weight, and Q is the charge. So then the vacuum is invariant under the SL2 curves U1 symmetry. Using this property, we can just determine the correlators on the plane. And from the plane, then you can perform a large warped conformal transformation. Namely, this will change the global properties, and it will bring you from plane to a thermal cylinder with where this tau has now periodicity. And then you will find this thermal correlation function, and this describes this has the same structure as the complex SYK correlation function around the saddle point. This is the first observation, and then you can also consider small warped conformal transformations that doesn't change the circle. Say, I do perform this function f, sorry, f bar. I wanted to indicate that we are doing the Euclidean theory, but I forgot to change all the f to f bar. But this is this is in Euclidean theory. Now, if we keep fix the circle, namely keep fix the periodicity beta, and perform only this warped conformal transformations, which is periodic in tau, and also the U1 phase parameter also has the same periodicity. Then such or such small Virasoro-Kazhmoudi perturbations can be described by basically if you write this Virasoro generator, you can find this Schwarzen term and again a UN term. So if you look at this Virasoro zero mode on a fixed background and consider the small Virasoro Casamudi transformations, and that's also an effective action, and that can be compared to the SYK effective action. And if we identify this parameter C over K, where C is the central charge and K is the level of warped CFT, with the ratio between heat capacity and the charge this parameter gamma and K. If you identify the parameters like this, you'll find that the zero mode generator energy is the same as the SYK effective action. Okay, what else? So for warped CFT, it's a two-dimensional field theory, and you can put it on torus. And then you can, very similar to the derivation of Cuddy formula, you can perform a warped modular transformation. Then you'll find that this warped CFT partition function, it's not modular invariant, but modular covariant. It really looks like the weak Jacobi. This partition function looks like the weak Jacobi, and then you can write down an analog of the Cuddy formula, and this was given by this DHH formula. It contains two parts, and one part really looks like the Kerr half of the 2D CFT with U1 Casamudi current. And the as left part here, I didn't write it down, but this one is proportional to the expectation value of the U1 field. It's it does not have this square root structure, but we can see that this SR part, which looks like which is the same as the Kerr half of the CFT with U1 Casamudi, also can be matched to the SYK entropy. So here, let me briefly comment. So the entropy of SYK that derived from this effective action is actually the entropy deviation from the zero mode, from the zero temperature entropy. SYK model also has a zero temperature entropy, but what I compared here is not that, it's the deviation. And this part agrees with this warped CFT, basically the Virasoro part of the warped CFT. And it's also for warped CFT, it also have the similar property that as left part is basically describing some zero temperature entropy, and as right part is describing the excitations. So this matching really describes the same thing. They're both describing the excitations from extremality. Okay, so what else? We can also consider the vacuum character of warped CFT. This is basically the Virasoro-Kazmudi character. And from that, you can also calculate the corrections from the Virasoro-Kazmudi descendant to the pattern function, and that also agrees with the one loop correction in complex SYK. So to summarize, it seems that complex SYK model can be understood as a symmetry broken phase of WCFT, and we have described the following similar properties. That finished the two parts, and now let's talk about gravity. So we know that pure Einstein gravity in 3 dimensions, we can consider the solutions in the Feldman-Graham gauge, where rho is the radial direction, and the metric can have a expansion with the leading term G0, which is the boundary metric, and G2 basically is the stress tensor. And these solutions is fully characterized by the arbitrary boundary metric and the stress tensor, and the stress tensor satisfy these constraints. So, so for Brown-Hanot boundary condition is a special case of imposing the Dirichlet boundary condition, which is to fix the boundary metric and then allow fix the boundary metric and allow the stress tensor to be arbitrary. And then you'll find that the asymptotic symmetry are 2 copies of Virasoro, and with Brown-Hanot central charge given by the length and the gravitational coupling. So we can consider a generalized boundary condition. First, we need to describe the phase space by considering certain, by putting the theory on arbitrary boundary metric. Now we parameterize this boundary metric by a dileton, by a wear factor phi, which we assume only depend on x plus. Well, more generally, it will also depend on x minus. And then with 2 additional parameter functions of x plus, mu plus and mu minus. If we consider this mu plus to be 0, that basically gives back to the this warped CFT phase space. You can solve the constraints and work out the variational principle. Basically, from the variational principle, you can read this mu minus and mu plus are the sources, and L minus and L plus tilde. These two functions are holomorphic, and these 2 are the corresponding sources. And then you can impose boundary conditions from here that is compatible with the variational principle. Here, if you don't do anything else, the natural thing is to fix mu minus and mu plus, then this will give back to Brown-Hanot boundary condition. On the other hand, you can add a Lorentz violating boundary term to the action, and so basically that's G minus and O minus are source and well from one side, and this is like performing a Lorentz transformation, and you swap the role of source and well, and so now you will have instead of directly like boundary condition, you have a mixed boundary condition. In the plus set, you are still imposing directly boundary condition, while in the manner set while imposing this Neumann boundary condition. And if you do so and impose these new sources are fixed, then we'll find the asymptotic symmetry is a very thorough Casimudi algebra with a central charge. That's the same as the Brown-Hanover central charge, and a Casimudi level, which depend on the expectation value of one set of your stress tensor. So this is still the old CSS boundary condition that is proposed to do to the warped CFT. Now we need to deform this warped CFT phase space a little bit and impose the generalized boundary condition. And that is basically, instead of having mu plus to 0, we have finite mu plus, and still add this boundary, similar boundary term, and we'll find that the symmetry is broken to 2 U1s. So here is the picture of the 3D theory. We have the throat, we have warped CFT, and that has mu plus equal to 0. And if we turn on mu plus, and we flow to a theory with only 2 U1 symmetries. That breaks this symmetry. And then we can do a dimensional reduction. And then the 2D theory has metric, dileton, and gauge field. And it has the general solutions can be worked out. Basically, it has 2 types of solutions. The most general one is the so-called running dileton solutions. And if we look at some special limit that correspond to the extreme of black holes in higher dimensions, you'll get this constant dileton solution. And on top of that, you can consider perturbations, and that's the RJ flow solution. And this RJ flow solution, if you consider doing an IR perturbation, is described by a function nu. This nu is basically the linear dileton coefficient, and it satisfies a familiar equation which comes from a Schwarzian action. So here's the picture in 2D gravity, and this road, this near ADS2 region now is described by this, is basically driven by this small perturbation parameter nu. And if we work out the effective action, you'll find that it's Schwarzian plus this U1. And then here's the result. And we can also compare this effective action derived from this 2D holographic renormalization to SYK, and have the following dictionary. And this is all compatible with the earlier description of warped CFT and is mapping to the SYK model. So, okay, so here is the full picture, and I guess I'm running out of time, and so I will not repeat myself. And finally, I'd like to advertise an upcoming paper with, again, my brilliant student Boyang Yu and Alejandro Castro, Victor Godet, and John Simon. And this is about considering perturbations in four-dimensional gravity, and which glues the perturbation at the near horizon throat to perturbations in the full Kerr region. And that's all. Thank you for your attention.
Okay. Thanks to Songwei. Any question or comment?
So you mentioned the zero temperature entropy. So you mentioned that when you do the compare with WAPT CFT, you disregard that part. But when you do the comparison with the 3D gravity or 3D reduced to 2D gravity, is there any hint what is the identification of that zero temperature entropy?
Well, because as we mentioned that the SYK really describes the perturbation from zero temperature. So if we want to map to SYK, we consider the deviation away from the zero temperature entropy. And then if you look at the zero temperature entropy, you look at really the slot itself. And then the black hole entropy can be nicely described by the Cardy formula or WAPT Cardy formula of this of WAPT CFT itself. It contains so this is sort of a unified picture. At the throat, you can using the WAPT CFT, you can reproduce the zero temperature entropy, and then you can also deviate away, and that's also calculate the deviation, and that deviation part can be matched to the SYK. SYK itself doesn't so far doesn't have the description for the zero temperature entropy of the black hole. SYK does have a zero temperature entropy, but that's not to be matched to the zero temperature entropy of the black hole itself.
Okay, thank you.
Could you go back to the slides that you computed the entropy in warp CFT?
Yeah.
Yeah, in this formula, the thing in the square root is negative.
Oh, no, it's not. It should be positive. But A is negative. It's
could
it's
you
due
remind?
to some weird convention, basically.
So what's A?
A is the it's a parameter of the circle. So this the torus is specified by the spatial circle and the thermal circle. And we're in Euclidean space. So this it's a bit weird notation. That this A is something like -1.
Okay, I see.
More question? Okay, same time is out. Let's thank the speaker again.
Thank you.
So
Okay,
our second speaker.
We still have
Sure.
5 minutes.
Okay.
Yeah, could you make me a co-host?
Yeah, sure.
Okay.
Yeah, I think.
Good. Could you see the slide?
Yes.
Okay. Yes.
Good.
So.
Wait. Sorry. I cannot.
Yeah. That's the.
Yeah.
Okay. Our second speaker is Chiming Chang from Tsinghua University. and he will talk about the exotic consistent 1+1 dimension anomalies, a ghost story. Yeah, please.
Okay, good. Yeah, okay, first I would like to thank the organizer and give me this opportunity to speak. And so I've never visited Fudan before, and so this time I can visit Fudan virtually, but I hope I will have opportunity to really physically visit Fudan in near future. And this talk is based on a paper with Yinxian Lin, and he's a postdoc at Harvard. Okay. Anomaly, the study of anomaly has a very long history, and there's an important milestone of this study of anomaly is the West-Zumino consistency condition. And this condition basically tells us that the anomalous transformation should be compatible with the symmetry algebra. And this consistency condition of anomaly together with some local properties of anomaly led to the descent equations and a cohomological classification of perturbative anomalies. And this was by Stora, Zumino, and there is a more recent review by Harvey. And so this is a screenshot of West-Zumino paper, and we can see that it's almost 50 years old. And there is a more modern perspective of anomaly based on the inflow paradigm by Colin, Cortis, and Harvey. And the inflow paradigm says that anomaly in D dimension is the inflow of a classical action in D+1 dimensions. And based on the inflow paradigm, there is a very natural question you can ask, is that can we classify anomaly using inflow? And so this has already been shown to be, it is known to be inadequate for conformal or wild anomalies. So for conformal and wild anomalies, we do not know how to find out, we do not know whether there is a classical action in D+1 dimension that inflow the D-dimensional anomaly. But the inflow paradigm is usually assumed to be true or to be okay for Topf anomaly of internal symmetry or space-time symmetry. Topf anomaly is a control breaking of symmetries in QFT. The meaning of this is that if we say consider partition function of the QFT on some background I denoted by phi here, and this phi can be either metric, gauge field, or some other background fields. And phi transform under some background transformation I denoted by lambda, and lambda can be background diffeomorphism, background gauge transformation, or some other transformations. And the partition function is not invariant under the background transformation. So this phi with superscript lambda denotes the background field phi after the transformation lambda. And the partition function is not invariant. So z of phi lambda is not equal to z, but with a multiplication of the phase. And so it's called control breaking because this violation of the symmetry is very mild and just by a phase multiplication of the partition function. And the inflow paradigm says that we can write down, or there exists a D+1 dimensional bulk classical action. And if we compute the partition function of this bulk classical action, so that meaning just take E to the bulk classical action, then the transformation law of this bulk partition function and basically transform with an opposite phase. So that if we consider a combined system, that's the bulk classical action plus the boundary quantum field theory, then this combined system is free from anomaly. And inflow paradigm says that there's always such bulk classical action that you consider combined system, then there's no anomaly. And so based on the inflow paradigm, we can try to classify the d-dimensional, classify the d-dimensional anomaly by classify the d+1 dimensional bulk phases, because the anomalous phase of them are just related by a minus sign. And when d+1 equals 1, 2, 3 dimensions, the bulk phases are classified by a group homology, and this was done by the work of Chen, Gu, Liu, Wen, Kong Wen, and Wen, and some many other papers. And when d+1 equals 1 to 6 dimensions, the bulk phases are classified by cobordism group. And this is based on the result of Kapustin, Fried and Hawkins, and Unikura, and many others. And this result, some part of it assume the bulk reflection positivity. And there are also some more general setup, that is, suppose we have a slightly severe breaking of symmetry such that partition function transform not just by a phase, but transform, say, like a vector, finite dimensional vector. And we actually have a partition vector instead of a partition function. And in that case, we can also try to find out a vector. I mean, we can also try to find out some classical action that also transform like a vector, and then cancel the anomaly. This is more general anomaly, and these are the topological order, and this was classified by this paper, or studied by this paper. And let me try to be more specific and consider a simple setup that's 1 + 1 the QFT with a U1 symmetry. And I would restrict the QFTs to define on Riemann geometry without imposing other structure, meaning that we consider non-spin QFT, and we can define the theory without specifying the spin structure. And in this case, the partition function transform like a scalar under the symmetry. And the background field we consider here are the background metric, background spin connection, and background curvature. And we also consider there is a U1 symmetry. So there is a background U1 gauge field and the field strength of the U1 gauge field. And in this setup, the 1 + 1 dimensional anomalies are inflow by a bulk 2 + 1D Chern-Simons action. And for the gravitational anomaly, we have the gravitational Chern-Simons, take this form. And the gravitational Chern-Simons just, you can construct it by consider the spin connection omega and take omega d omega plus 2/3 omega cube. And this as your Lagrangian density. And so the Chern-Simons level here, if you want to cancel the 1 + 1 dimensional anomaly, you pick the Chern-Simons level here to be the anomalous coefficient of the 1 + 1D gravitational anomaly. And similarly, the 1 + 1D U1 anomaly can be canceled by 2 + 1D U1 Chern-Simons action. And again, the U1 Chern-Simons level, you just pick it to be equal to the anomaly coefficient, the U1 anomaly coefficient in 1 + 1 dimension. And it's well known that the Chern-Simons level, for the Chern-Simons action to be well defined, the Chern-Simons level are quantized. So this translates to the quantization of the anomaly coefficient in the 1 + 1D. So here I will just quote the result from the computation. And the result is that the gravitational anomaly coefficient kappa r squared should be a multiple of 8, basically 8 times the integer. And the anomaly coefficient for the U1 symmetry, kappa f squared, should be an even integer. And so these are the general discussion for QFT. And if we consider 1 + 1D CFT, the anomaly coefficients are also related to the stress tensor two-point function coefficient, the leading coefficient in the TT two-point function, and also the leading coefficient in the JJ OPE. And so the coefficient of TTOP, the leading coefficient in the TTOP is the central charge, and the kappa R square is basically related to the difference between the left moving central charge and the right moving central charge. And the U1 anomaly coefficient kappa F square is related to the difference between the left moving level and the right moving level. However, this classification is actually challenged by a very simple 2D CFT. That's the holomorphic BC ghost system. And let me review some basics of the holomorphic BC ghost system. And it's a free theory. And the fields in this theory are free Grassmann fields denoted by B and C. And they have this very simple action, B partial bar C. And this action is the same as the action of a holomorphic fermion or a wild fermion in 1+1 dimension. And the conformal weight of, or holomorphic conformal weight of B and C are given by HB equals lambda and HC equals 1 minus lambda. Lambda here is the free parameter of the BC system. And when lambda equals 1/2, you basically recover the free fermion theory. But in general, lambda can take other value, and you have a more general theory. And this system, BC ghost system, has a U1 ghost number symmetry. And that basically just rotate B by some phase and rotate C by the opposite phase. And the current of this U1 ghost number symmetry basically given by B times C normal order. And as I said, that this U1 symmetry just rotate B and C by opposite phase. And that basically, in other words, that tells us that the ghost number or the U1 charge of B and C are given by -1 + 1. And we can also very easily write down the stress tensor in terms of the B and C ghosts. And they are given by this formula. And so as we can see that the holomorphic conformal weights of B and C ghosts are, they depends on the parameter lambda. And when lambda is an integer, that tells us that the holomorphic weights of them are both integer. And in this case, since they are holomorphic fields, so they do not have anti-holomorphic weights. So the holomorphic weights are basically just their spin. So when lambda is an integer, the spin of B and C are both integer. And then the BC ghost system can be defined on arbitrary Riemann surfaces without specifying the spin structure because they have integer spin. And then we can compute the central charge or the chiral central charge in this theory. So because we consider holomorphic theory, so the chiral central charge would just be given by the holomorphic central charge. And using our previous formula for the stress tensor, we can compute the TT OPE and pick up the leading coefficient, and that gives us this formula. And then we can specify lambda to be an integer, and we find out that the chiral central charge should be -2 plus 24 times the integer. And similarly, using the formula that I showed on previous slides, we can compute the chiral level K minus, and K minus equals 1. So we can see that the chiral central charge of the BC ghost system, holomorphic BC ghost system, and the chiral level are incompatible with the quantization of the Chern-Simons level that we just shown. So recap that the chiral level should be 8 times the integer, and by the Chern-Simons quantization, and also the chiral central charge should be an even integer. And we can see that neither the chiral central charge or the chiral level satisfy this quantization condition. So the goal of today's talk is that first I will try to show you a classification of the TOF anomaly from a purely 1+1D perspective instead of a 2+1D perspective classification by inflow. And then I will show you that the holomorphic BC ghost system, the anomaly of it actually satisfy this classification of TOF anomaly that is purely from the 1+1D perspective. And then the second part of this talk, I will switch gear and talk about a mixed anomaly, a mixed U1 gravitational anomaly in 2 dimensions. And then I will discuss the relation of this mixed anomaly to an anomaly called the isotopy anomaly for the topological defect lines in 2 dimensions. Okay, so the part 1.
Just wondering if you impose further unitarity, is there any violation of the previous pattern?
We will see. I will discuss that in later. And it turns out, okay, the BC ghost system is a non-unitary theory, and it violates the quantization condition for from Chern-Simons level. And again, I will discuss later that if we consider unitary theories, I can show that they will actually always satisfy the quantization condition from the Chern-Simons level. Okay.
Okay, thank you.
So let's go back to our traditional roots and study the Wess-Zumino consistency condition. And it turns out that we actually need to use a slightly general version of Wess-Zumino consistency condition that we call the finite Wess-Zumino consistency. And the finite Wess-Zumino consistency condition basically boil down to the commutativity of this diagram. So suppose we start with a partition function and then do a background transformation by lambda 1 and get this partition function, and then following by another background transformation lambda 2 and get this partition function. And the resulting partition function should be the same as the partition function that we consider a background transformation with the parameter being the composition of lambda 1 and lambda 2. And the commutativity of this diagram basically give us this rule of the phases. So the brown phase basically is the phase that generated by this brown arrow, and this red alpha is the phase generated by this red arrow, and also the blue one is the phase from the blue arrow. And so for the diagram to commute, then the phase should this combination of phase should be 2 pi times the integer, such that if you exponentiate that just gives you 1. And we can actually take the infinitesimal limit of the parameter lambda, and this will reproduce as the original Wess-Zumino consistency condition. And besides the finite Wess-Zumino consistency condition, we also need another ingredient from locality. And locality basically amount to these 2 conditions. So first, we want to assume that the anomalous phase alpha is the local functional of phi. And second, if the background transformation lambda is infinitesimal, we want to further assume that the anomalous phase is a local functional of both phi and lambda. And also alpha should vanish if lambda is alpha should vanish if phi is a trivial background. So we can argue the second locality condition by the following argument. So first, let's consider a trivial background. And then so let's consider some conserved current of the symmetry. The current should conserve away from any other operator insertion. And that basically means that in correlation function, if we consider nabla mu j mu, then with some other operator insertion, then this correlation function should be just equals to some contact terms on trivial background. So if the second locality condition is false, and then the anomalous wall identity will actually explicitly violate this structure. So you will find out that nabla mu j mu with some other insertions correlation function will have some non-contact terms on the right-hand side. And the first locality condition can be think of as an extrapolation of the second locality conditions to the case you have non-infinitesimal lambda. And these two locality conditions can be actually stated in a more precise way as the following. So here I use this curly G to label the space of background transformations, lambda. And in general, the space of all the background transformations will form will have many kinetic components, and I denote them by Gn. And G0 is the one that is the kinetic component that contains the trivial background transformation. And so here I introduce a notation AI. So this denotes a basis of local functionals, and that vanish when you take phi equals 0. Basically, that means trivial background. And the above two locality conditions boil down to this formula, that the anomalous phase should take the form like this one. So let's try to check that this formula indeed satisfy our previous locality condition. So first, this formula is a local functional of the background phi. So you can see indeed is a local functional of phi. And the second condition is that when lambda is infinitesimal, and then the anomalous phase should be a local functional of both phi and lambda. So if lambda is infinitesimal, then that means this label n should be 0, because because G is the one that contains the trivial transformation. G0 is the one that contains the trivial transformation. And then, so phi 0, we also assume phi of 0 is 0, so we do not have this term. And then we have a sum of a basis of local functionals of phi and lambda. So this checks the second locality condition. Good. And so we have the finite West Zumino and the locality condition. So let's try to apply this condition to the 1 plus DQFT. And actually, I would study only the 1 plus 1 DCFT. So first, let's try to study the gravitational anomaly. So for simplicity, let's consider the 1 plus 1 DCFT on a flat torus. And in this case, we have a large diffeomorphism. And the group of large diffeomorphism is SL2Z. And by locality, the anomalous phase should be, anomalous phases are constant. So basically, that's because there's no local functional that you can write down. And that's because we choose to put our theory on flat torus. So the metric is just flat. And I mean, the spin conduction and curvature are both 0. And so the only terms we have in the anomalous space is this theta. And so under SL2Z transformation, and in general, we will have this transformation law, and with a phase that depends on the group element of SL2Z that's specified by 4 integers A, B, C, D, and satisfy the equation that A times D minus B times C equals 1. And here we actually implicitly assume that the partition function does not vanish identically for all torus moduli tau. That's because if partition function just vanish, then this equation is actually trivial. We just have 0 equals 0, and and we cannot use that to constrain phi. Constrain theta. And the solution to the finite Wess-Zumino consistency condition is.
Can I ask a question about the previous slide?
Sure.
So, to what extent it relies on the series conformal? It seems to me that the equation is also true. The structure is true for like TT bar.
The theory. You mentioned. Okay, let me first explain where I assume the theory should be conformal. That's because if you do a large gauge transformation on a metric of a torus, and usually, and then in that case, the torus metric would change. So the torus metric depends on the torus moduli tau. So tau will transform like this, but there's also a wild factor, a constant wild factor of the metric. And then you need to assume that you have a CFT and then to scale out the wild factor. And then go back to a metric that depends on the transform tau. About the TT bar theory, I'm not sure about that. Okay. Good. So so basically we can take this ansatz and then try to check that the commutativity of the triangle diagram I showed previously, and then that will give constraint on the theta. And here I would just basically show you the solution. And the solution of finite Wess-Zumino basically given by the group cohomology H1 PSL2, Z, U1, and it's isomorphic to Z6. And let me explain this formula a bit. So first, we have PSL2Z instead of SL2Z. That's because there's a Z2 part in the SL2Z that will not act on the torus moduli tau, so it will not be involved in this formula. So the symmetry group we have is actually PSL2Z. And the coefficient of this cohomology group is U1. That's because our partition function are complex number, so they and the phases are they transform by a phase, so that's why the coefficient is U1. And the closeness condition of this cohomology basically is equivalent to the finite Wess-Zumino consistency condition. And you also have the exact you impose the closeness condition and model the exact part. So the exact part corresponds to you do some trivial redefinition of the partition function. Good. And let me try to give a more detailed description of this Z6. Let me show you what's the generator of the Z6. So first, the general anomalous phase are basically determined by the phase under the S transformation and the phase under the T transformation. And they are basically given by these two formula. And the generator of this Z6 corresponds to theta S equals pi mod 2 pi, and theta T equals pi over 3 mod 2 pi. And the phase under the T transformation is related to the chiral central charge. And for this, for the generator of Z6, we will find out that, and if we plug this condition in this formula, we will find out that the chiral central charge should be -4 plus 24 times the integer. And so we have the generator of Z6, and we can apply composition to get all the elements in Z6. And let's focus on any odd element of Z6. And that will basically corresponds to our previous theta s and theta t and multiplied by an odd integer. And in this case, we will see that, we can see that theta s is also pi mod 2 pi. And from the formula of theta t, we will find out that the chiral central charge is a times the integer plus 4. So, and from the formula of theta s, this implies that at the s invariant point, basically the square torus, the partition function should equals to 0. That's because from our previous anomalous transformation formula of partition function, we know that the partition function should, under S transformation, will transform to minus itself. And but if we consider the S invariant point, square torus, we also know that the partition function should transform under S to itself. So we have an equation that's Z equals minus Z. So that basically tells us Z equals 0. And the square torus is also symmetric under the refraction of left and right. It's basically refraction along this dashed line. And if our CFT is refraction positive, that means that will tell us that the correlation function or partition function on symmetric configuration should be positive, and that applies to our case here. But we also know that partition function is 0, not positive, so we know that the chiral central charge cannot take a times AZ plus 4, so that basically tells us the chiral central charge should be a multiple of 8 for refraction positive CFT. And this quantization condition agrees with the one from the Trans-Simons level quantization. And our previous analysis applied to the case, there's an assumption that I mentioned that the partition function should not vanish identically for all tau. And so what if the partition function vanishes identically for all tau? And in this case, instead of consider partition function, we can consider 1-point function. And the solution, there's a similar finite Weis-Zumino consistency condition for the 1-point function. And the solution to the finite Weis-Zumino in this case basically is given by the good cohomology, this one. And the only changes is that instead of PSO2Z, we have SO2Z here. And as isomorphic to Z12. So I will not do the detailed analysis, but this Z12 actually tells us that a quantization condition on the chiral central charge that says chiral central charge should be an even integer. And we can, so I would not prove this here, but by some analysis, we can also show that if the chiral central charge is 4 times the integer plus 2, then, it's not a multiple of 4, but a multiple of 4 plus 2, then the CFT must contains Grassmann value operators. So the CFT must be, in some sense, a ghost theory. And we can just see right now that recall that previously when we consider the BC ghost system, the chiral center charge is -2. So this agrees with the quantization condition here. It also agrees with my statement that the theory must be a ghost theory. So now let's come to the analysis of U1 anomaly. And again, let's consider CFT on a torus. The space, in this case, the space of U1 gauge transformation lambda has many kinetic components, and the kinetic components are labeled by the winding number around non-contractible cycles. I denote it by CI, and it's just defined here. I integrate the D of the gauge transformation along a non-contractible, along a vector of non-contractible cycles. We get the vector of winding numbers. And in this case, the anomalous space is more interesting. It takes this general form. And let me explain this formula a little bit. So first, let's focus on these two integrals. So these two integrals are basically related by integration by parts. So we can, so F is dA, we can try to do an integration by part and to move this term to the previous term. And that will give F prime times d lambda A. And the reasoning of writing down this formula is that we try to use integration by part to put everything that's possible to the term with a field strength F. And so the function of this function F here is a periodicity function of our gauge parameter lambda. That's because our lambda is a periodic variable. So so if F explicitly show up in the integrand, I mean if lambda explicitly show up in the integrand, and it should sit inside a periodic function, or inside the form like d lambda. And finally, we have also this function theta. That's a function of the winding number only. So next, for simplicity, we would restrict to we would do some further restriction on the background. We would like to set the background field strength equals 0, F equals 0, so that this term actually do not contribute. That's why previously we would like to consider integration by part to put all the possible terms into the form that there's an explicit F show up. Okay. So next, let's try to check the commutativity of this triangle diagram. And again, I use colors to organize the faces from these different arrows. And the finite Weiss-Zumino consistent condition basically tells us that the faces, this particular linear combination of the faces, should equal 0 mod 2 pi. And we can reorganize previous equation in this form. So I first collect all the terms that does not involve any any integrals. And then let's first focus on these two integral terms. And so first, we notice that because the background gauge field A and our gauge parameter lambda 102 are arbitrary, so the second and third term should vanish identically, and that will actually tell us that this function kappa should actually be a constant, and that can be identified with kappa f squared. And also we left with the equation on the first line. And in the first line, this omega denotes the intersection matrix that basically given by this integral here. Okay, so let's focus on the equation we left, and specialize this to a torus. So we have two winding number, MA and MB, and I pick the intersection matrix of a torus to be 0, 1, minus 1, 0. So this equation can actually be explicitly solved, and I give the solution here. And we can see that, so theta should take this form, and also the equation would tell us that kappa f squared should be an integer. And there are still two unknowns in this formula, theta 1, 0 and theta 0, 1. But actually, if we consider the mixed finite Wess-Zumino, basically, if we if we try to consider this diagram, but some arrows are diffeomorphism and some arrows are U1 transformation. If we consider that case, then this will allow us to also fix the theta 1, 0 and the theta 0, 1 and get this relation. They are related also to kappa f squared. So the analysis phase for the U1 case are basically completely determined, and the coefficient kappa f squared is an integer. So let me give a short summary here. And first, because that when we discussed in the intro part of the talk that the inflow paradigm plus the Chern-Simons level quantization give us that the anomalous, the gravitational anomaly coefficient kappa r squared should be a multiple of 8, and the U1 anomaly coefficient kappa f squared should be an even integer. But as we just seen, from the finite Wess-Zumino consistency condition, that gives us a strictly weaker quantization condition, and that only requires the kappa r squared to be an even integer and kappa f squared to be an integer. And this weaker quantization condition is saturated by the holomorphic BC-GO system. And we can also explicitly compute the anomalous phases in the holomorphic BC-GO system and explicitly check that the holomorphic BC-GO system also, satisfy the finite Wess-Zumino consistency condition. And along the way, we also show that if the chiral central charge is not a multiple of 4, then the theory must contain ghost. And if the chiral central charge is not a multiple of 8, then the theory cannot be reflection positive. Okay. So let's turn to the second part of today's talk, the mixed gravitational anomaly in 1+1 dimension. The holomorphic BC-GO system has a U1 ghost number symmetry. And this U1 ghost number symmetry has a pure U1 anomaly and also a mixed gravitational anomaly. So it can be seen from the CFT data. And this anomaly shows up in the OPE between the stress tensor T and the ghost number current J. And so the TJ OPE has this leading singularity kappa. So the coefficient I denote by kappa FR. And this kappa FR is related to the parameter lambda in the BC-GO system by this formula. And if lambda is an integer, meaning that both B and C have integer spin, and in this case, kappa FR should be an integer over 4. So, so there are a couple of different ways to see this mixed gravitational anomaly. So first, if we can try to compute the number mu J mu of the ghost number current, then we can see that the current is not conserved on a non-trivial background. So number mu J mu equals to, if you have non-trivial field strength and non-trivial curvature, then number mu J mu is not 0. And also, if we try to integrate this equation on some Drano-Riemann surfaces, this will tell us the U1 ghost number symmetry is only conserved up to a background charge that's proportional to an Euler number. So these are all very basic. You can find them in Poczynski chapter 5. The perturbative Wess-Zumino consistency can be solved by descent. And so the descent equation basically tells us that the descent equation is the equation is the equation that we would like to find a closed and background gauge invariant four form that satisfy the equation like this. So first, the four form should be locally exact. So this four form J4 should be exterior derivative act on the three form J3. And if we consider the background variation, background transformation of J3, and this should give us exact three form. That's a D of a two form, and the two form is related to is proportional to number mu J mu. So so to check the perturbative Wess-Zumino consistency condition for the mixed gravitational anomaly, so it's amount to try to solve this equation. We can try to plug this formula, the thing on the right hand side, to the descent equation, and then try to find out the closed and background gauge invariant four form J4. And so there are some literature says that, I mean, this descent equation has no solution, and but we can actually find out a solution to this descent equation, but there's a very peculiar property of the solution that is in the four form. In order to write down this four form, we actually need to use the epsilon invariant symbol of 1 plus 1D, this epsilon AB. And this epsilon AB basically explicitly break the 3 plus 1D or the 2 plus 1D Lorentz invariance. So let's see the solution. So the solution is basically given by F wedge epsilon AB RAB, and we can see that the 1 plus 1D invariant symbol explicitly show up here. And so let's check that this four form indeed satisfy the descent equation. So first, the four form can be written as D of this three form here. It's easy to see that if you take exterior derivative of the first term and the second term, you will basically get the four form. And there's an ambiguity in this descent three form that's given by an exact term. And this ambiguity is related to the fact that you are allowed to add local counter terms. And so and also we can take a variation, background variation of this descent three form, and it's also not hard to see that this will give us a D of a descent two form, and the structure here also appear in the nabla mu J mu. So with the solution to the descent equation, we have the descent 2 plus 1 form, and the descent 2 plus 1 form can serve as the Lagrangian density of the bulk 2 plus 1D classical action for the inflow. But epsilon AB here that sit inside the descent 2 plus 1 form will break the 2 plus 1D Lorentz invariance. So in order to use this to write down an inflow action, we actually need to pick a special direction. So we consider a 2 plus 1D spacetime manifold M3 that basically is given by M2 times a half line from 0 to infinity, and this half line gives us this preferred direction. And then we can write down this inflow action. So we have epsilon AB, omega AB wedge the field strength, the U1 field strength F. And this action is actually the famous Wenzi topological term that's relevant to the Hall viscosity in non-relativistic quantum Hall system. And so here we would like to propose a slightly different inflow mechanism that will actually preserve the 2+1D Lorentz symmetry. The proposal is the following. We would like to match the 1+1D spin connection with an 2+1D SO2 gauge field, I denoted by AR, at the boundary partial M3. So that's basically the 2D spacetime. And with this, we can write down basically the standard mixed Chern-Simons action. We have the U1 gauge field A, which D of this SO2 gauge field AR. And AR is matched on the boundary M2 with the spin connection by this equation. And the coefficient 1/4 here is determined by trying to matching the flux quantization condition on both sides. So with this mixed Chern-Simons action, we can demand that we can use the old argument, and then that will tell us that the Chern-Simons level should be quantized, and more explicitly, the quantization condition is given by here. Kappa FR should be integer over 4. And we can check that the BC-GO system indeed satisfy this quantization condition from the Chern-Simons level. So let me give some remarks on this. So it may be possible to derive the quantization condition of the mixed anomaly coefficient, kappa FR, by finite Weisel-Minor. However, in order for kappa FR to appear, it's necessary to go to the background beyond flat torus, and we leave these for future work. And secondly, if we consider a general CFD with the mixed anomaly, and we have TJ OPE with the leading coefficient alpha, and T-bar J-bar OPE with leading coefficient alpha bar, the mixed gravitational anomaly is given by the sum of the leading coefficient alpha and alpha bar. So the sign between the alpha and alpha bar is plus sign instead of minus sign. So it is not like for the pure anomaly. For pure gravitational and the pure U1 anomaly, we have the differences between the left moving quantity and the right moving quantity. And this is just some curious observation. We so far do not know how to make use of this. And finally, if we have a theory with a non-zero mixed anomaly, then by this OPE, the TJ OPE, they will tell us that the current J is not a primary operator. And so there should exist some weight zero operator that's not a descendant operator, because and then J will be the descendant of such weight zero operator. But CFT cannot be both. Such CFD cannot be both reflection positive and compact. So this argument tells us if the mixed gravitational anomaly is non-zero, then the CFD will be either not reflection positive or non-compact. I think I'm be run out of time, so I will skip the part that relate the mixed gravitational anomaly to the isotopic anomaly of topological lines. So I would actually jump to the conclusion. So here is again the summary of what we find. We find a strictly weaker quantization condition than the one from Chern-Simons level, and we find out that the holomorphic BC-GO system indeed satisfied this weaker condition, but it does not satisfy the stronger condition from Chern-Simons quantization, except for the mixed anomaly coefficient. And so one interesting question to ask is that So we use we use Trent-Simons action to be the 2+1D classical action to do the inflow, but we can see that we cannot reproduce the anomaly of the holomorphic BC ghost system. So the question is that, is there a new 2+1D classical action that can be responsible for the anomaly of the BC ghost system? And there's a classification of 2+1D non-spin invertible topological order using the diffusion category by Kong and Wen. And this classification shows that the chiral central charge should be 2 times the integer. And this is a good sign that it agrees with our quantization condition. However, there is no known non-spin invertible topological order that actually realize the minimal central charge case, C minus equals plus or minus 2. Okay, I will stop at here.
Okay, let's thank the speaker. Any question or comment?
May I have a question?
Sure.
Is there any explanation why the Trent-Simons inflow paradigm not valid for this gross-spanning fields with gravitational anomaly?
I think basically that's, for us, it's just a fact that the BC ghost system does not satisfy the quantization condition of the Trent-Simons action. But maybe one way to see why is that because the BC ghost system first is non-unitary and also it's a ghost system. So maybe that can explain why it's not captured by the 3D Trent-Simons. But we do not have a more intuitive way to understand why 3D Trent-Simons cannot capture the anomaly for BC ghost.
I see. Thanks.
So I'm wondering, in the later part, you mentioned mixed anomaly. If you consider the torus partition function, which is twisted by this U1, and then do ST, can you say that?
So you need to have, okay, let's see. So because I think you need to have either non-trivial curvature or non-trivial field strength in order to probe this mixed anomaly. And if you consider flat torus, then there is no non-trivial curvature. And if you also impose flat U1 gauge field, then you cannot probe the mixed anomaly, unless you assume there are some non-zero U1 field strength. But even in that case, I'm still a bit doubt that you can really probe the mixed anomaly in that case. So I really think that we need to go to higher genus in order to see or apply finite Western minnow to constrain the anomaly coefficient.
I'm not really convinced because just for what you just said, because here the equation, what you wrote is a local equation. It's a derivative of J. But if you consider partition function, it's like, you do some kind of integral. Perhaps, background flux is enough. But I'm not pretty sure.
Yeah, you mean background U1 flux?
Yes. Then if you twist by that one and then do the ST transformation.
Yeah, that may be we haven't started seriously in that case.
Yeah, or what I'm just want to say is that here the local equation, what is said is true. Locally, you want to see it, you need the curvature. But if you consider twisted partition function, it's like you do more integrals.
when you say twisted partition function, you mean you consider still flat background gauge field, but you twist it by some anatomy. Is that what you mean?
Yes.
No, I don't think it's enough. That's because if we look at our this general ansatz, sorry, yeah, here. So we consider flat torus and also flat U1 gauge field, and that will basically tell us the A is 0. So there's no first term. The only term you have is the second term. But the second term is the one that we've already studied. And the second term does not contain the kappa FR.
Okay, thank you.
More questions? If no, let's thank Jimmy again. And so we finished the first section. Let's have a break. Let's come back at 4:30, right? 4:30. Okay.
We should start the second shift this afternoon. In this second shift, we have only one speaker. The speaker is Matthew Henner, come from Max Planck Institute. His talk is about complexity and conformal field theory. Let's welcome.
Hey, very good. Thank you for the invitation. Thank you for the opportunity to give this talk. What I want to cover is a series of works that I have written with various collaborations during my tenure here in Germany, in Potsdam at the Max Planck Institute for Gravitational Physics. And let me start with a small introduction. So the topic of, or like the broad topic of this development is an interface between gravitational physics, quantum field theory, and information science. So basically the topic of this workshop. And well, saying this in, or putting this in other words, it's about viewing fundamental interactions through the lenses of quantum many-body systems, quantum many-body theory. So when one talks about this broad research area, then inevitably the common topic is the notion of entanglement. And this notion is a quantum many-body notion that specifies how difficult it is for a given quantum state to be represented on a classical computer as a tensor network. And well, I mean, I probably don't have to introduce really the notion of a tensor network. The one that will be of some interest for the purposes of my talk is this mirror tensor network that has drawn a lot of attention in the context of holography. What I want to emphasize is that past year 2004, we've witnessed a lot of results on entanglement entropy in quantum field theory. And this included universal results and tools in two-dimensional conformal field theories, right? And in ADS-CFT, entanglement entropy is manifested as a Bekenstein-Hawking entropy of certain codimension 2 surfaces, the Ryuta-Kanagi surfaces. And well, as you have seen in, or will see also in this workshop, it became a new quantitative tool for quantum gravity, in particular, leading to resolution of one aspect of the Hawking information paradox. But what's important for me is that when Ryu and Takanagi proposed the gravity dual to entanglement entropy, it was already understood due to earlier developments by, in particular, Cardi and Calabrese, but also by Woolsey and collaborators, and even earlier papers, of what really entanglement entropy in quantum field theory in general and in conformal field theories in particular is. The topic of my talk today is kind of entanglement entropy, but in the reverse. So the motivation for my talk are new quantum gravity observables that were proposed in a series of papers by Lenny Susskind and collaborators, as well as in later papers. That what differs from in the way in which they are different from entanglement entropy is that entanglement entropy is a codimension 2 quantum gravity observable in the bulk of a holographic spacetime, and these ones are going to be codimension 1 and codimension 0. So these quantum gravity observables are known under the name of holographic complexity proposals. There are at least 3 of them. So the idea for one is that this is the ADS3 solution depicted here that represents the ground state or time evolution or time development of the ground state of 1+1 dimensional holographic conformal field theory. This is the asymptotic boundary. The boundary of the cylinder is the asymptotic boundary where the quantum field theory lives. If one picks a constant time slice on the boundary, that defines the state in the path-physical formulation of quantum field theory. And then the idea of these new gravity observables is kind of similar to an entanglement entropy idea, holographic entanglement entropy idea, which is to consider geometric notions that are uniquely picked, or that are picked by the choice of the constant time surface on the boundary. And these 3 geometric notions are first, maybe let me start from backwards. So like the simplest one that you can consider is basically to say that the gravitational theory is causal. So one can consider a causal region associated with this choice of the constant time slice on the boundary. So this is this causal diamond. And then one thing that one can do is to evaluate the volume of this codimension 0 bulk object associated with this constant time slice, so associated with the space, with the state in quantum field theory. And this is this complexity equals volume 2.0 proposal. The other quantity that you can do is to evaluate the gravitational action in this null region. And this is the complexity equals action proposal. And then there is like yet an alternative proposal that goes under the name of complexity equals to volume, which is to consider this time slice, consider all codimension 1 spatial surfaces that are anchored on this constant time slice on the boundary, and maximize the volume. And you want to maximize the volume because this direction here is time-like. So if you sort of push this surface in the time-like direction, then you basically lower its volume, and as a result, the maximum volume is going to be something like the one that I drew here. Now, these surfaces, similarly to holographic entanglement entropy, they are divergent. So like all these quantities, actually, they are divergent. So the volume, the spatial volume of this surface is divergent. The space-time volume of this causal diamond is also divergent. And this comes about because of the asymptotic region of untitled geometry. What I want to emphasize is that these quantities diverge in a particular way, right? And also they behave in a particular way when you probe various interesting spacetimes. So one interesting spacetime to which you can apply these quantities, right? Because there are nothing else than just ways of probing various holographic spacetimes, is an anti-de Schwarzschild black hole. So like this is the eternal anti-de Schwarzschild black hole. This black hole is dual to a thermal state in your favorite holographic quantum field theory. And that's when you look only at one asymptotic region. When you look at both asymptotic regions, this black hole represents a thermal field double state in now 2 copies of your favorite holographic quantum field theory. And when you look at this quantity, and this is probably like where the most famous property of this holographic complexity proposal is that if you look at all these 3 proposals, in the black hole spacetime in which you sort of push this two time slices upwards, then it turns out that as a function of the time variable, which is like the sum of the time on the left and time on the right, all these quantities exhibit a linear growth as a function of TL plus TR. So all these quantities are basically proxies of the growth of the Einstein-Rosen bridge in the black hole interior. And as a result, like, are interesting quantity from the point of view of fundamental properties of black hole physics. So this is something that made quite a splash in our community. And of course, like, there are many other properties that you can emphasize. Like, one property that I want to pay some particular attention to is that if you take like this black hole spacetime, evaluate for so to speak, like TL plus TR equals to 0, the value of these quantities, and subtract from it twice the value of these quantities evaluated in empty ADS spacetime, and you subtract twice the value of these quantities because this spacetime has two asymptotic regions, and the subtraction regulates the result and yields it UV finite, then the answer that you get is going to be proportional to the thermodynamic entropy. So I'm going to denote these properties 1, 2, and 3, and I will come back to them throughout my talk. Because what my talk is really about is the field theory, the dual field theory interpretations of these novel gravitational observables. And as their name suggests, these novel gravity observables were conjectured to be related to the hardness of state preparation in dual quantum field theories using limited resources. So as I said, there are these 3 holographic complexity proposals: complexity equals volume, complexity equals action, and complexity equals volume 2.0. The perspective that I want to advocate for this emerging or emergent field is that before holographic entanglement entropy was proposed, we already had some understanding of entanglement entropy for quantum field theory. In particular, quite a lot of things that became, like a canonical information or canonical properties of entanglement entropy were already known there in the context of quantum field theory. But it's actually quite different when it comes to complexity in quantum field theory. In fact, before these proposals were postulated, we did not have any example of complexity calculation in quantum field theory. And this talk will describe basically first efforts to introduce and understand such a notion. So that's a good place to pause and ask if there are any questions, like quick questions, 1 or 2, about the basics.
Just wondering, the internal black holes, this linear increasing, this length was recently interpreted as island, things like that. But is there some connection between?
I would say that perhaps like this is a good question. I mean, I would probably postpone it till later discussion because it would require probably some elaboration and back and forth exchange. But like let's come back to this later. Okay, thanks. Okay. Anything else? Okay. So let me outline the general idea. So the general idea comes from the works written in a somewhat different context by Michael Nielsen that were concerned about quantum computing in qubit systems. And before we move on to the many-body quantum physics, let's focus on a simple example that is actually very telling, that I very often use to illustrate this general picture, that actually made it eventually to a paper written by Brown and Saskind last year. So in whatever I have to say, I will primarily focus on complexity of states, but you can also talk about complexity of operators. And the idea is that we want to define, well, we are given a state that we're going to be calling a target state, and we're going to be given a state that is considered a simpler state for some reason, and this reason might be also subjective. And we are also given limited resources, right? So let's consider a situation in which our quantum mechanical system is a 1-qubit system. So it's a 1-spin system. And a reference state is a state in which a spin points along the x direction. And the target state, so the state that we want to obtain from a reference state, is a state in which the qubit points along the z direction. And the resources, let's not talk about limitations now, that we are given are rotations along all 3 axes that are generated by Pauli matrices, of course. So if we want to go from the reference state to the target state, as given here, there are infinitely many possibilities, right? But one possibility that's gonna occur to us immediately is to rotate by an angle pi-half along the y-axis, right? Like that's like probably the most standard thing that occurs to everyone. But there, as I said, like there are infinitely many possibilities, and a competing possibility is to first rotate along the z-axis by say pi-half, and later evolve by another pi-half along the x-axis, right? And if you were to quantify the hardness of these 2 tasks, it could be natural to assign such a hardness to the angle that, like to the angle by which we rotate, perhaps modulo 2 pi. And if one were to do this, over here on the left-hand side, we rotated by an angle pi-half. And on the right-hand side, we rotated twice by an angle pi-half. And in the end, like over here, we had to do sort of less rotation than here, right? So naively, following this, this proviso, we would say that this operation is more complex than this one, because here we have to do simply more infinitesimal rotations. Now, this is true, but this is true if we make some choices. And the choices that we make here is that the cost of doing rotations in all the directions is the same. It doesn't have to be like this. It may be for some, say, experimental reasons to be much harder for us to rotate along the y-axis and much easier for us to rotate along the remaining 2 axes. And if this is the case, for example, like if this rotation is 10 times harder, then the right way of accounting for cost using this logic would be to put a factor of 10 here, and here leave the sum unaltered. And in this case, actually, this set of 2 rotations would be an easier choice to do than the rotation that normally would yield as the simplest. And I'm not really, showing this in vain as a curiosity, but actually I'm showing this as a formulation of the problem of state generation, starting from some state that we're going to call simple, using limited resources, because this kind of approach that was here applied to a setup in which there are 2 states and 3 possible generators of unitary transformations generalize in a very natural way to quantum field theories on the lattice. So basically, the way to view it then is to think about the target state related to the reference state by a unitary transformation. And later I will have like a little bit to say about the situation in which this transformation is non-unitary. Now, this transformation that we're going to apply, we're going to represent as a circuit. So it's going to be like an exponent, path order exponent. And each layer of the circuit is going to be decomposed into generators applied with some velocities. so that like the generators in the case of the rotation were simply Pauli matrices, and these velocities were basically infinitesimal, were basically the rate of infinitesimal rotations. And once we do this decomposition, we can define the cost of a circuit by looking at each layer. So that requires integrating over this parameter tau that represents the circuit. At each layer, we're going to take like absolute values of the velocities with which we apply generators. We're going to sum over all generators, and then we're going to account for possibility of penalizing some generators with respect to the others. So for example, in this case, all these penalty factors, so I was running over 3 indices, like this epsilon I was corresponding to rate of rotation in the X, Y, or Z direction. And these pi I, in this case, were taken all to be equal and set, for example, to 1. It doesn't really matter if they're equal to each other. But in this case, the pi, the penalty factor associated with the Y rotation was 10 times higher than the factors entering for X and Z rotations, right? So like that's roughly speaking the logic. So this is a cost function. And the complexity can be defined as a minimum of the cost function, right? And the cost function that sort of has like the simplest relation to counting of something is this cost function that is based on the L1 norm, but you can also define cost function based on the L2 norm. And one can also define like another kind of cost functions, for example, based on the Fubini steady distance, and I will come back to them later in the talk. So basically, what I presented to you here is a general framework that can be applied to a quantum many-body system. And the quantum many-body system of interest is going to be a quantum field theory on the lattice. And when you want to apply this framework to quantum field theory on the lattice, then you basically encounter several interesting questions that you have to answer in order to be able to make progress. So one question that you have to address is, for quantum field theory, what to take as a simple reference state. Now, on this simple reference state, we're supposed to ask with a circuit composed from some elementary transformations. So the question is what to take as these, right? Then this circuit that I present here is a unitary circuit, assuming that all i's are Hermitian operators. And the question is, shall we focus only on unitary transformations, or perhaps we should also, include other types of operations? And the reason why one might want to generalize from unitarity is that in quantum many-body systems, a very powerful method to use is Euclidean time evolution. And Euclidean time evolution certainly includes a component that is non-unitary. Now, the target state that I assumed so far was pure. The question is, what happens if you consider a mixed state? And of course, when we deal with quantum field theory on the lattice, as we take the lattice spacing to be finer and finer, we are led to UV divergences, and the question is how to deal with them, and also before, like how to count gates. So like these are like the five most important challenges that arise when you try to apply this idea to the setting of quantum field theory, and my talk will discuss them basically one by one. Are there any questions so far? Good. So if there are no questions, let me proceed. So what I will show you in the coming several minutes are the results for free quantum field theories, including free conformal field theories. And later on in the talk, I will show you results that are more streamlined for conformal field theory that sort of justify the title of my talk. And the results I'm going to be discussing were presented in 2017 in a series of works, including papers, including these two papers. So let's start with a vacuum. So as I said, like we're going to be considering free quantum field theory. So imagine that like you take a target and a reference state as a ground state of two quantum field theories on the lattice, and these quantum field theories are going to have two different masses. So like say the reference is going to have like a mass m1 and the target is going to have like mass m2. And what we want to do is we want to put these theories on the lattice and UV regulate it, right? And when we do this, the beauty of this of free quantum field theories is that the ground state of free quantum field theories are Gaussian states, and on the lattice we can go from one ground state to another by applying Gaussian transformations. That is, transformations that are quadratic in fundamental variables, which are pi and phi bosonic fields for free bosonic quantum field theory. So the idea is to use as generators of elementary transformations the generators of this Gaussian transformation. So for example, like it's gonna be operators like phi 1 squared, where 1 is the number of lattice side, or for example phi 1 pi 3, where phi 1 is the field on the first lattice side and pi 3 is the momentum operator on the third lattice side, etc., etc. And these guys form for n lattice sites. These guys form SP2n group, and to calculate complexity, what we do effectively is to define a metric on this group and find geodesics. What's important for us is that there are many choices to make. However, you can make some choices that brings you to the result that does not look too dissimilar from the result of holographic complexity proposals. And what I want to say is that the guidance here, because these were the first works on this field, was not really to be guided by some deep microscopic understanding, but actually to try to reproduce the features of holographic complexity calculations. So in particular, if you go through these steps, the answer for complexity in starting from the quantum field theory ground state on the lattice at one mass and the quantum field theory ground state on the lattice at the other mass, so these are reference and target states, is given by this expression. And if you look at this expression, it turns out that this expression does not diverge in a way similar to holographic complexity proposals. But actually, it turns out that instead, if as a reference state, you take a state, you take a ground state of a quantum many-body system that does not have the kinetic term for the field, so that's not going to be a relativistic quantum field theory, there's going to be some deeply non-relativistic system, a set of harmonic oscillators at each lattice site, then when you do this, it turns out that you're able to reproduce the features of the holographic, the leading divergence of holographic complexity proposals. And despite the fact that this calculation was a free quantum field theory calculation, you might try to invoke some notion of a universality to argue that similarly to entanglement entropy, for complexity, the structure of divergences might exhibit some sort of a universality shared between strongly and weakly or even free quantum weakly coupled or free quantum field theories. So you can move on and play the same game for a thermal field double state. It's a bit more complicated, and you can have a look at the paper if you're interested in details. But it turns out that, again, of course, you reproduce the structure of divergences. And this is relevant for the vacuum. And again, when you look at this formula in which you look at the complexity of the t = 0 thermal field double state, then subtract from it twice the result of the complexity for the vacuum, you are able to reproduce using free quantum field theory calculation the fact that this expression can be proportional to the entropy density, or actually to thermal entropy. So what I'm saying is that the free quantum field theory calculations can be quite telling when it comes to holography. However, when you try to apply it to time dependence, then it turns out that the story is less rosy, you're not really able to reproduce the long-time growth of complexity in free quantum field theories. Actually, our choices of complexity lead to a saturation of complexity quite quickly on, and the saturation of complexity can be understood as dephasing of various oscillatory contributions. And the argument that we want to provide is that, well, I mean, it is while it is in stark contrast with holographic expectations, it should not come as a surprise, because we know from other quantities that theories at weak coupling and theories at strong coupling behave very, very differently when it comes to their time dependence. And the key quantity to consider in this context is the shear viscosity. At strong coupling, the ratio of eta over S is 1/4 pi. At weak coupling, it is a quantity that effectively diverges. So it's not surprised that time dependence of complexity looks very differently in free quantum field theories and in strongly coupled quantum field theories. Okay, so to wrap up that part of my presentation, what I discussed so far were first applications of the idea of complexity to free quantum field theories, including conformal field theories on a lattice. These calculations used unitary gates, and for bosons, these were, say, products of field and momentum, like quadratic products of field and momentum operator, like among all the lattice sites. For certain fine-tuned cost functions, we are able to get exact results for complexity. The downside of these calculations was that these circuits used also very non-local gates. And example of such a gate would be like the field operator acting here and a field operator acting in other galaxy. Like that was like the downside of these studies. And the important factor for maybe the rest of my talk is that when you look at states in quantum field theory, states are not really vectors, but like our vectors up to phases. And the story of complexity in quantum field theory persistently should neglect the phase contributions of circuits to the states, right? Because they do not really matter. Now, the good features of these proposals is that one can reproduce static properties of holographic complexity proposals, such as leading divergences in the vacuum, complexity of formation for thermophile double states, complexity of purification for subregions, so like that I will mention later. The bad but expected is that they lead to a very different time dependence than holography. And I would say that this is okay. This is something we have to live with. But the really problematic feature of these calculations was that these calculations do not naturally generalize to holographic quantum field theories. So what I want to discuss in the remaining 15 minutes of my talk or so were examples of holographic complexity consideration, examples of quantum field theory complexity considerations that actually have a chance of generalizing to the holographic CFT. So this is a good time to pause and ask if you have any questions about this free quantum field theory consideration.
Excuse me, Professor?
Of course. I can hear.
So, yeah, I have a very basic question. So it seems that the complexity is defined for a state, but you have a target state, a reference state. So the complexity is defined for a pair of states?
Okay, very good. So thanks for the question. So there are two kinds of complexity that one can define actually. Let me go back to the basics. So over here, I was discussing a situation where we have like reference state and target state. We consider all operators that take us between these states, and we decompose these operators into circuits, right? So actually, what I was secretly doing here was to define a complexity for an operator, right? Because I take some operator, I represent it as a circuit, and I assign a cost to the circuit, right? And then I minimize over circuit. But when I do minimization, I have to supplement this minimization algorithm with boundary conditions, right? And the idea for a boundary condition is that you want to study with, you want to start with an identity and finish with and then now you have a choice, because you can either finish with a unitary that prepares for you a target state, or you can finish with an arbitrary unitary that you wish, right? And what I want to say is that there's going to be many unitary transformations that prepare the same target state. For example, like over here, I talked about, well,
Right.
there are two circles, but in general, you can, you know, like you can always have like a unitary that acts trivially on a target state and multiply your desired unitary by it from the left, right? And that's going to produce for you another unitary transformation that gives you like the same target state. What I'm saying is that the complexity in this way of phrasing things, the complexity of operators is a more primitive notion that you can use to define a complexity of states by supplementing a set of boundary conditions for the target unitaries, right? You can also define a notion of complexity of states that does not require you to define a complexity of unitary transformation. It's just applicable for states. And such a notion is the Fubini study complexity. And actually, I'm going to just describe it in a sec.
Okay, thank you.
Okay.
Thank you for the question.
Excuse me. Perhaps I
Yes.
have a very basic question. Does complexity depend on the reference frame? Because the reference state and the tangent state will change in different reference frame.
Let me see if I understand. So complexity is like complexity of states is defined as a functional of reference and target states, right?
Yes, but reference state will change in the different reference frame.
Well, I have not really invoked the notion of reference frames in this discussion. I guess like the way I would like to think about it is that somebody gives us a target state, or like we are interested in studying a particular target state, for example, the vacuum of a conformal field theory, and you want to obtain this particular state from some reference state. And now like this reference state is like your cheap resource, right? And it's also given to you. It's a matter of convention what you call a cheap resource. For example, like in the context of the tensor network, like this cheap resource are states that have low or even no entanglement, right? Such states are called product states. And this Mera tensor network can be thought of as a quantum circuit, discrete quantum circuit that takes this cheap resource and using limited transformations, which are just two types of unitaries, prepares for you something that is very close to the target state being the ground state of the critical Hamiltonian, right? So, I mean, I would not really invoke like any notion of like frame dependence of states, etc., etc.
Okay.
I would say fixed reference, fixed target.
Oh, okay. Thank you, Professor Matthew. Is there any question?
Yes, please go ahead.
Okay.
Okay. Okay. So if there are no questions, I'll continue. Oh, sorry. Or do you have a question yourself? Maybe I misunderstood. Oh,
I have a question.
Oh, please go ahead. Sorry. Yeah.
Oh, sorry.
Go ahead.
On page 5. Please show page 5. Kerr. We know complexity can be defined for an operator or for a state. So we think that those two definitions are equal. But my question is, are those two definitions equal? Are those two definitions are equivalent for any conditions?
Well, I would say thank you for the question. So what I would say is that there are many different definitions of complexity that you can adopt. What I would say is the notion of a complexity of a unitary operator does not really require you to invoke any notion of state. So like you don't, when you talk about complexity of unitary transformation, you say somebody gives us a unitary transformation. For example, such a unitary transformation is this rotation, right? And now we're asking about like all possible decompositions of this rotations into circuits, assigning cost to each such a decomposition and minimizing over such a cost. And that's it, right? Now, when you invoke the notion of complexity of state, now you can do two things. So one thing is to come up with a cost that is really tied to a circuit acting on your reference state. And such a cost is going to be given by the Fubini study metric that I will discuss in a second. But the other choice is to use this notion of unitary complexity to consider all unitary transformations that take us between a reference and target state. And for each of these transformations, define a complexity of the unitary, and now minimize over all unitaries that realize this passage from the reference to target state. And this is basically what I've been discussing here.
Thank you. Thank you.
Thanks for the question.
Thank you.
So
what questions? Okay.
So in lieu of time, I mean, I will proceed, and of course, like there's going to be plenty of time later to ask questions. So let me remind the last sentence that I said, which is that all that I told you so far was interesting because we were able to reproduce certain features of holographic complexity proposals using free quantum field theory calculations. However, free field theories are not really the quantum field theories for which the standard two-derivative classical gravity holography works. So what we want is we want to have a framework that is a more streamlined framework that applies to more general quantum field theories. And here, of course, it's very hard to make a general progress. However, the important observation that is due to earlier papers, including papers by Javier Magan and Paolo Saputa, or the papers by Alex Bellin, Gabor Rossi, and Aitor Levkovic, or papers by my collaborator Mario Flori, was to look at conformal field theories in 2 dimensions and define complexity associated with their stress energy sector, which is a vector of Virasoro group. So this is something that is universal up to, what the central charge is for all conformal field theories, regardless if they are holographic or non-holographic. And this is the topic of the 2 papers that we've written together with Mario Flori. I'm just gonna provide a bird's eye view on these papers, and I want to encourage you to watch an excellent seminar that Mario gave in our group recently that cover these 2 papers in great depth. And of course, after this talk, I'm gonna send the organizers the slides. So the setup that we adopt is a setup that originates from this paper, and it is to consider a 1+1 dimensional conformal field theory on a Lorentzian cylinder. So this is a 2-dimensional conformal field theory in Lorentzian situation on a circle across time. And we're gonna be assigning complexity to unitary circuits or unitary circuits acting on states that realize the diffeomorphism of this circle in a gradual form. So this spatial circular coordinate sigma is going to be going to f of sigma in a gradual way, where tau is going to be our circuit parameter. So at tau equals 0, like we're not going to be doing anything. And where tau equals, for example, 1, that's our choice, then we're going to be obtaining the final diffeomorphism. And such circuits, as is written in these papers, are realized by unitaries, in which what one does is one exponentiates left or right moving component of the stress tensor of your conformal field theory, and the stress tensor components of conformal field theory are applied with some particular velocities that are related basically to a time derivative of this f function. So this is the setup, and now of course, like this is one layer of the circuit. This one layer of the circuit we want to think of as you know, sum of elementary generators times the velocities, one choice that you can make is to claim that, okay, my elementary generators are going to be the stress tensor generators at a given spatial position, and I'm going to count how many times each of them was applied. That's one possibility, but there are other possibilities. And the possibility that I want to discuss briefly is the notion of the Strubini study complexity. So this is going to be a complexity that is sort of intimately tied to the circuit acting on a state. So what we're going to be doing is we're going to be basically taking, you know, like this, we're going to be taking some reference state. So the reference state that we're going to be picking is going to be the energy eigenstate of the CFT Hamiltonian. On this energy eigenstate, we're going to be acting with the circuit that we're interested in. And when t equals to 1, then we're going to be getting a target state that is given by the transformation that generates for us, you know, like this diffeomorphism, and as a result, it's going to generate for us some particular combination of descendant states starting from this H, right? But you know, this is a circuit, so we can slice it in a sequence of. I mean, this is going to give rise to a sequence of states, and the sequence of states is going to interpolate between the reference state, energy eigenstate, and the target state that is going to be this unitary transformation acting on H. Now, these states, of course, live in a Hilbert space of your CFT, and as a result, this Hilbert space induces for you the notion of a length that is given by the distance in Hilbert space set by the scalar product between vectors. Such a distance in Hilbert space is known as the Fubini study distance. And now, when the dust settles and you do this calculation, you end up with the following complexity functional for your complexity problem in two-dimensional conformal field theory that is effectively given in terms of the two-point function of the stress tensor in a state H. And you can think about minimization of this functional as a geodetic motion in which this sigma, so the spatial coordinate of your quantum field theory, acts as a label of coordinates. This f of sigma is a coordinate, and this tau is a parameter along the geodesic that tells you like where you are in some auxiliary metric, and this auxiliary metric is given in this form. And when you consider this cost functional, then effectively what you're counting are some notion of applications of Virasoro generators. Anyway, I mean, there are two take-homes from this discussion. So one take-home is that if you want to make progress and understand holographic complexity, perhaps like the simplest way to approach it would be via two-dimensional conformal field theory, where there are universal results associated with the Virasoro algebra. And what these papers with Mario Flori exemplify are various ways of assigning costs to conformal transformations and to Virasoro generators or stress tensor that generates these generators that actually do make sense and do give rise to well-posed minimization problems. So normally I would ask a question, but in lieu of time, let me finish the talk. What I want to say is you can apply similar considerations to what I have described before to mixed states as well. So let me discuss this very briefly. There are three papers that I have in mind. What I want to say is that the first paper that I will be discussing is a paper we've written with Hugo Camargo, Rob Jefferson, and Hannes Knaute, who are members of my group. And actually, this paper received a crucial boost during a wonderful discussion and hospitality that I was welcomed with at Fudan University when I visited it in March last year. So actually, this paper is very much tied to Shanghai. And the idea there is related to this path integral optimization. I will not really say much about it, but for those of you who heard of it, it's a way of preparing states, including mixed states, using path integral language. And what we showed in this paper, using similar techniques to the ones applied in these works, was that you can think about this path integral optimization program as applying circuits made from exponences of stress tensor components in conformal field theories. And the only difference is that these circuits are no longer unitary circuits. In particular, the energy density, so something like T plus T bar in these programs is applied as a Hermitian, rather than unitary transformation. And what we showed in this work is that you can apply a technique of circuit complexity to explain the path integral optimization. So basically, path integral optimization is not really like a standalone approach to complexity in conformal field theory or in quantum field theory, but actually it's nothing else than just gate counting as described so far in my talk, with the exception that you have to open up and allow for non-unitary transformations. Now, when you want to discuss complexity of mixed states, you don't have to open up to the notion of non-unitary transformations. You can also use complexity of pure states. And what you have to do is you have to consider a mixed state and all its purifications. That is like all pure states that live in large Hilbert space that represent the mixed state as a reduction. And once you formulate the problem in this way, you can obtain the complexity of, you can define a complexity of purification that's going to be nothing else than a notion of complexity applied to mixed states that utilizes the pure state complexity. And this is what we did with Hugo Camargo, Lucas Hack, Alexander Yan, Tadashi Takayanagi, and Bennett Vint in a paper that appeared in September this year. And in this work, we focus on conformal field theories and also try to compare with holographic complexity proposals applied to holographic mixed states, noticing a lot of similarities. So it's time to wrap up this talk. So let me start by saying that complexity is a genuinely novel notion in the context of fundamental physics. So first applications to gravity date back to around 5, 6, 7 years ago. And similarly to the history of entanglement entropy, complexity arose in black hole studies and is now an emerging subject in the context of quantum field theory. So entanglement entropy in quantum field theory was born in 1986 in a paper by Bombali et al., which later resurfaced in a paper by Srednicki, and like both of these works were concerned with free quantum field theories. And remember that in my talk I also started with free quantum field theories. Then there was a paper by Holtze, Wilczek, and Larson, in which they consider for the first time entanglement entropy in conformal field theories. This discussion was streamlined 10 years later by Cardy and Calabrese. The results by Cardy and Calabrese, which were making waves around that time, were taken up by Ryu and Takayanagi in their proposal to define entanglement entropy in ADS-CFT. An important breakthrough came in 2013, where Lukovic and Malosena proven using path integral formulation of holography, Ryu and Takayanagi proposal. And another 6 years later, Pennington and Larry and collaborators, including Harry Maxwell, who gave a talk, I guess, yesterday at this workshop, use these developments to resolve an aspect of information paradox in ADS black holes. Now, what I discussed today is a survey of first works explaining complexity in quantum field theory. This is basically the timeline. So what I want to say is that we're probably going a very similar route as the story of entanglement entropy in quantum field theory and gravity. However, the rate of progress is much faster, in a sense that every year we are really observing important breakthrough. So this is basically, you know, the 20 years that were needed to progress from, you know, complexity in free quantum field theories, from entanglement entropy in free quantum field theories to entanglement entropy in gravity. And well, I'm like, this is like 2 years that were needed to go from complexity in free quantum field theories to some notions of complexity in conformal field theory. So what I want to emphasize is that the rate of progress in this field is actually, you know, quite steep. And well, I mean, like, if there's one thing that it suggests is that there's exciting future ahead for complexity in quantum field theory and gravity. So this is all that I have to say. Thank you very much for your attention and questions, and sorry for running a bit over time. Thanks.
Oh, thank you. Any question?
Hello, I have a question.
Oh,
In respect of the complexity of purification, how can you be sure that you find all of the purification of a density matrix?
No, that's a very good point. So actually, we're not sure about it. What we did is we look at. Yeah, so let me go back. So the important aspect of this paper that we wrote in September is that we focus on free conformal field theories, and we look at so free boson and free fermion conformal field theories, and we look at density matrices in a situation in which they are described by they are Gaussian mixed states. And for these Gaussian mixed states, we look at purification that are Gaussian pure states. So like that's the restriction. And now what we see is that if we consider a system of say 10 sites in your quantum field theory in the lattice, we don't see a difference when it comes to the quality of purification of purified complexity if we purify to 20 sites in total, or if we purify to say 25 or 30 sites in total. So it seems that, you know, if we restrict to Gaussian purifications, sort of minimal Gaussian purification to the systems that are twice as big as the original subsystem seem to be sufficient to reach the minimal value. Now, my co-authors have written a paper in which they in which they describe numerical methods that underlie our studies, and at least in the context of another quantity, entanglement of purifications, they were providing indications in which which were sort of pointing in the direction that, at least for entanglement of purification, if you purify your Gaussian state to a non-Gaussian mixed state, the optimality, the optimal purification is going to be actually Gaussian, right? So sort of like enlarging purifications to non-Gaussian purification is an orbital. You don't have to do this. Now, for complexity, I don't have an argument in this vein. However, in this work with Tadashi and collaborators, we're comparing this entanglement of purification with another approach that Tadashi and collaborators proposed, which was this symmetric optimization. And despite the fact that we're using like Gaussian setup, we were able to reproduce these more general results applicable to any conformal field theory. So, I mean, I would say that despite the fact that this is really restrictive, and you're right, I mean, one probably should worry about it. I mean, in the cases that we consider, we did not really find indications that this was really the limiting factor in our studies. But it was a very good point. Thanks for bringing this up.
Okay, thank you. Thank you very much.
Sure, my pleasure.
So, what questions?
I have a question.
Please go ahead.
Is in your page 11. Page 11.
Yes.
yeah, here. Yeah, here you consider the two-dimensional conformal field theory. My question is, if we consider the boundary conformal field theory, I mean, if we consider a closed string, and I mean, I consider 2D brand, consider closed string propagating from one brand to another brand to express this process. To express this complexity. I mean, this boundary state as one of boundary state as the reference state and another as the target state. That's my question.
I mean, I guess that's an interesting point. I think it's not really the point that I had in mind when I discussed this. So for me, like the reference state was the state in the Hilbert space of your full conformal field theory, and the target stay the same. What you're talking is something different. I mean, one may wonder if you can apply. I mean, like you might say, okay, I consider two-dimensional. I mean, I consider string theory. String theory is described like two-dimensional field theory. How the notion of complexity manifests itself in the context of string theory. I think this is a good question to ask. I think related questions were asked in the context of entanglement entropy recently. So entanglement entropy in string theory.
Entanglement entropy. That's boundary state.
But I mean, unfortunately, I don't really have any sort of like a closed answer, apart from saying that this is an interesting question to ask.
Okay, thank you. And another question is in this unitary operator, the exponential part. As I know, in Nielsen's geometric approach, his exponential part expressed as Hamiltonian, and here you view this Q as I mean, it's a generator expressing this energy momentum tensor. So, does this? But in his geometrical approach, he explained this velocity along this along this path. This path. Does this the same thing or different thing?
Okay, very good. So Nielsen's approach is very much rooted to preparing unitary transformations in quantum computing. And well, the way you want to do this is using Hamiltonian time evolution, right? Now, in the context of that's a very good question. So in the context of these three, I mean, in the context of free quantum field theories, we were completely fantasizing in a sense that, you know, like we were talking about some very general transformations that were given by quantum circuits, and these layers of these circuits were not necessarily Hamiltonians in a sense that they were not necessarily operators that had spectrum bounded from below, right? However, so what I'm saying is that like this is a valid approach. You can do this, but you might have a hard time realizing this in a quantum many-body system as time evolution. Now, there is this other approach that is like very much rooted in this path-integral optimization, which is really concerned about time evolution. In this case, Euclidean, but you can also try to generalize it to Lorentzian one, which is, as a result, very close to the notion of, you know, like Hamiltonian time evolution, right? So what I would say is that in this respect, this path-integral optimization and related approaches are perhaps kind of closer to what Nielsen had originally in mind. And I would also say that it's a development in a very positive direction, because maybe it wasn't really apparent from the summary part of my talk, but you know, like if you want to prove anything in holography, you have to prove it using the central holographic identity, which is equality of gravitational and field theory partition functions, right? And the interplay between these two is given by the notion of the sources in quantum field theory, right? Which translate as asymptotic boundary conditions for gravitational theory. And the sources for quantum field theory, when you just talk about the stress tensor sector, is the metric in which quantum field theory lives, right? So what I'm trying to say is that the essence of this path integral optimization is to tweak the sources in your conformal field theory in such a way that you generate the circuit consisting of exponences of stress tensor operator in your quantum field theory that generates for you a desired conformal transformation, right? And such a conformal transformation can be time translation, or it can be something more funky, right?
Okay, okay. Thank you very much.
My pleasure. Thanks for the question.
So, more questions? If no, let's.
Sorry, maybe already forgot.
Okay.
Do you have further comments on this relation with island?
Yeah.
Oh, so were you having in mind the paper that Rob Myers and collaborators written, or?
I haven't yet read carefully. I'm just curious. In the simplest eternal black hole picture, there seems some relation there. Is there any sharp relation?
So what I would, I'm like let's see. I want to, now I can scroll back. So what I would say is that, well, I'm like, this is the eternal black hole. This black hole is non-evaporating, right? Because we have rigid boundary conditions on the left and on the right. So I would say that for this black hole, like this notion of islands does not really apply. I mean, there's so to speak, like no radiation that is escaping anywhere to a non-gravitational region. However, of course, you can adopt this setup to include evaporation as in the original papers on islands, and you can ask a question about like how about the notion of complexity. Yes. And my understanding would be that you would need to change the region that you consider because of the island emerging here in the middle, and you would have to modify your prescription for calculating holographic complexity. I have not done it. However, there are works that are concerned precisely about the interplay of islands and holographic complexity, and I would probably look into these works. I have not really worked on this. I think it's an interesting question. I'm also afraid that this is a question that is very hard to address using quantum field theory tools, because we're already having like a very hard time understanding this particular setup using quantum field theory tools. But as a long-term challenge, I think it's a very interesting problem to consider. And of course, you can ask questions of the kind like complexity of complex radiation, of Hawking radiation, and so on and so forth. And then like these things can be discussed and are being discussed currently.
Okay, thank you. If maybe one more, just short question. So you mentioned the mixed state.
Yes.
Complexity definition. So my understanding is that this complexity of purification somehow borrowed the idea from this entanglement purification. But if you have a mixed state, I can also do some other things like a canonical purification. You can define some reflected entropy. But then the question is, if I did a canonical purification, could I define or found some good complexity? Because then you don't need to do optimization.
Good. Okay. Very good. So thanks for the question. So yeah. So when you define complexity, you optimize over all circuits that take you from a reference to a target state, right? Now for purifications, there's additional issue, which is that when you purify, you're going to have like infinitely many states that are equally valid purifications in your mixed density matrix, right? So if you claim that there is a canonical purification of your density matrix, then you still have to find complexity and minimize cost functions applied to unitaries interpolating between your canonical reference state and canonical target state being canonical purification. However, you don't have to optimize over purification. So sort of like one layer of optimization is gone. And indeed, in this work, an important new problem with respect to earlier approaches. And I should also say that there was an interesting work in a very similar direction with some differences by Rob Myers, Shearer Chapman, and collaborators already a year ago. I have not really listed it here because I wanted to focus on this relation with conformal field theories. However, what I want to say is that in this work, and also like in this earlier paper by Rob and friends, the cruise of the problem was like also like this optimization over different purifications, right? So that's an important technical complication that you have to face for the COP. And indeed, like it's similar to EOP in this respect, right? I'm like maybe like I should add like one more thing on this vein. So previously at the beginning of my talk, I said that for certain very fine-tuned cost functions, you can get exact results for complexity. And what I mean is that you get a closed form expression for what is complexity as a function of some properties of target and reference space that are Gaussian. So what we are doing in our paper on purifications was to we only had to minimize over different purifications because we had a closed form expression for complexity between a reference state and a purification. We did not have to do any optimization there. We already had the result that included optimization that was analytic. If you were to discuss complexity of purification for mixed non-Gaussian states, it will be very different because we don't have a closed form expression for complexity for non-Gaussian states. So in such a problem that we are actually working on addressing now, you would have to do two complicated minimizations. So first, you would have to find a non-Gaussian purification. And for each non-Gaussian purification, you would have to find an optimal non-Gaussian circuit that prepares it. And then you would have to optimize over all purifications. So like that's a much harder problem. And this is something that we are thinking about. It turns out that it's also applicable to free quantum field theories. So for free fermionic quantum field theories, or for the Ising quantum field theory, if you look at, I mean, it's true that the quantum field theory is Gaussian, but if you look at reduced density matrix for two intervals that are disjoint, then it turns out that the reduced density matrix for two disjoint intervals is actually non-Gaussian because of the Jordan-Wigner strings that extend between these two intervals. And as a result, you'll have to, if you're talking about such simple setup applied to the Ising conformal field theory, you have to, and you want to talk about entanglement of purification or complexity of purifications, you have to adopt non-Gaussian methods. And this becomes actually quite interesting and quite hard. Yeah, this is something that we are working on with my collaborators as a follow-up to this work.
Thank you.
One more question.
Pleasure.
Of course. Yeah. So I see in this page you have listed many results for different 2D CFT, and my question is it possible to see some correlations with chaos quantity, for example, the OTOC in a 2D CFT for different model? I mean, for different model, you also have different behavior for the OTOC. So so is it possible to say some correlation between this complexity and the OTOC from this result?
Okay, very good. Thank you. So from these results, I would say no, because I would expect that the structure of UV divergences would be universal, in a sense that it would perhaps care about things like, you know, the central charge, etc., etc. I guess like the story is actually more complicated than this, but I would not. I mean, at least myself, I would not really be able to tell you like what's the correlation between these numbers and the chaos. And this is actually quite similar to the story that I outlined here regarding the agreement of, you know, the leading divergence of free quantum field theory calculation with holographic calculations, right?
Yeah.
You are able to reproduce the divergences despite the fact that one theory is chaotic and the other one is as not chaotic as it gets to, right?
Yeah. Yeah.
However, this feature of holographic complexity, this feature of holographic complexity, which is
the mutual complexity. You mean the mutual complexity?
Well, this is the complexity of a thermofield double state. So
I thought your mutual complexity means this. Okay, sorry. Yeah.
This complexity here is the complexity of a pure state that is described by a maximally extended ADS-fragile black hole, which is the thermofield double state in a pair of dual quantum field theories. So this long time growth of complexity is something that is very much tied to the spectrum of the theory, and it's something that might have a lot in common with the properties of chaotic correlators.
Mm-hmm.
But this is precisely the property that is very hard to reproduce from quantum field theory, because this is the property that is non-universal. And the results that I discussed were either the results that were universal because of the universality of the UV behavior of quantum field theory. So that was like basically the divergences of holographic complexity proposals and divergences of free quantum field theory calculations. And in the context of conformal field theories, I focus on the Virasoro factor, which is universal and cares only about the central charge. And central charge alone is not something that cares about chaos, right? Because you can take a stack of, 100, 1000 free boson conformal field theories, right? It's going to have a large central charge, but it's not going to be chaotic.
Right.
So I would say that like none of what I talked about so far is concerned or sensitive to chaos. And indeed, if I were to list like some like one of the biggest challenges for this field would be to move beyond universalities in the discussion of complexity.
I see. Thank you.
It was an excellent question. Thank you.
More questions? If no, let's thank the speaker again for his wonderful talk and wonderful answers. Thank you.
Thank you.